today we are going to dig deeper into the topic of model predictive control. Previously, we have mentioned about the optimal control problem formulation, how we can use them in our engineering problems, and maybe more importantly, how we can solve them. So today we are going to use this as a basis and go deeper in the direction of model predictive control. Model predictive control and the controllers that's designed based on this principle is quite important in terms of engineering, because nowadays with the improvement of computational hardwares and these kind of tools, they provide lots of or they find lots of application areas in terms of engineering today. But before going into the deeper in this area, let me briefly mention about the bigger picture. So in the last lecture, we have introduced the optimal control problem formulation and solution strategies, and this was based on the open loop control, I'm sorry. So this means that we have the model of the plant in hand, and then we determine the optimal control law based on this model directly. But what happens when the model or the original system changes, or we have disturbances or perturbations in between? So this may result in something like that. Let's assume that this is our diagram, this is time domain, and this is, let me say, the output of our system. And after designing an optimal control law, we were expecting such a system result, let's say. And this can be the reference signal here. But most probably, you're not going to get such a result due to several reasons. So the actual output of the system may be something like that. Maybe close enough to the original planned one, but not exactly the same. And there are some perturbations, ups and downs, and variations around the originally, let's say, expected signal. And most of the time, this is due to the lack of feedback loop in this case. But with the help of the model predictive control, we may get rid of these kind of things, because we are going to, let's say, consider the current status of the system in every optimization routine. So it's because of that model predictive control proposes quite large fields of application and provides quite nice results in terms of engineering. So this area became popular with more popular, let me say, with the introduction of the linear quadratic regulations in 1960s, and the studies of Kalman was, let's say, groundbreaking in this area firstly, and then found itself application areas in the industry in late 70s, and from that day on, increasing its popularity continuously. As I said, it's a kind of great competitor to the traditional control laws nowadays. And first of all, I would like to make an informal definition of a model predictive control. Let me write it again. Okay. In model predictive control, we are aiming to create a control scheme where we use a model of our system for predicting the future states that's going to happen. And we are not doing this for an infinite time horizon, for a, let's say, certain or finite horizon. So here, as I said, I was aiming to make an informal definition of this, and I have summarized the most important concepts for the model predictive control. So we are aiming to determine a control scheme for the system of interest, and of course we need a mathematical model of our system. And with using this, we are making a prediction. With using the model of our system, we are making predictions so that we have future states of our system, and we are not doing this for the infinite time. We are just making it for a finite horizon, like, let's say, 10 seconds in advance or so in future or so. Okay, so this is briefly what I would like to talk in terms of what is model predictive control. And now I was aiming to talk about the benefits of it. So because, as I said, in a repetitive times, this proposes us great benefits in terms of different fields. So First of all, it proposes us a proactive control action. So what is proactive control action? This means that we are able to consider the future disturbances and the variations in the set points or any other thing that may happen in our system. So this is a kind of great property. The other one is, let's say, flexibility. And by flexibility, I mean that the main approach is both suitable for linear and nonlinear systems. Of course, what you need to do in case of a linear system or a nonlinear system is slightly different than each other, but the main principles are there and you only need to make some minor modifications. And within the scope of today's lecture, we are going to mention more in the direction of the linear systems and, let's say, linear model predictive control. And of course, model predictive control will also give you, let's say, flexibility in terms of control objective. So this means that in the traditional control approaches, set point tracking is mostly considered, but in addition to this, you can also define an control objective or reference curve that fits into your scope better, so that you can enter this to your problem formulation and hopefully get better results. And the last thing that I could mention at this level is constraint formulation. And this means that, for example, if you have limits on your control system, you can enter this directly in your problem formulation, so that, say, system that please get away from the boundaries of my control signal, or you can also put some boundaries or constraints on your state variables or so that you have more flexibility digging deeper into the your system, and you will get more out of it at the end of the day. Okay, so this summarizes briefly the advantages of model predictive control. And now I would like to briefly talk about the main principle of the MPC, let's say. And the main principle of MPC can be summarized as plan for long term, but execute for one. So at this point, I would like to give an example from our daily life. So if you play chess, I think you will understand what I'm trying to say. In chess, you think the moves in advance, for example, the next 3, 4, 5 moves, sometimes 10 moves. But at a time, you can only apply one move. You make your move and then wait for the response of your opponent. If your opponent makes a different move for you, then in the next time frame, you need to run the same process again, consider the current situation and plan it for a long time, and try to find the best move for that specific time and only execute this best move. So this block diagram briefly represents the main structure of the model predictive control. Here, as you can see, we have our main process here, and at the end of the day, we need to apply a control input to it, and this provides us the actual output. And we are using this actual output as a kind of feedback to our model, which is represented here. And then this model basically creates us the predicted output of our system. But of course, in order to do that, it needs a control sequence, planned control sequence, and this planned control sequence is actually coming from the result of an optimizer. So we have an optimizer that considers the given cost function to it, and considers the given constraints to it, and proposes a new, let me say, optimal control law, and then we verify this over the results of our model. And as you can see, the model here plays a crucial role because we are mimicking the behavior of our actual process into this model. Of course, the more complex, most of the time, the more complex our model gets, we are coming closer to the actual behavior of our actual process, but then things may get complicated on the optimizer side. For example, when we have nonlinear two complex system models, then solving this optimal control problem on the background becomes a bit harder. It's because of that we need a compromise here. For example, if we have a good linear model of our process that includes most of the main behaviors, that's good, because then the optimizer can use this relatively simple model and create the optimal control law based on this model in an easier and less time-consuming way. And one of the main things that we need to consider within the scope of model predictive control is that we need to create this control sequence in every sampling time, most of the time, because we are going to apply this control at the current time, and then when one time stamp has passed, we need to repeat everything from the very beginning, considering the new outputs of our system, because we consider something, but anything may happen in between, or there could be a disturbance to our process. The output may not be exactly the same as we have expected, and we need to optimize it every single time frame again and again. And of course, some new terms are arising here, like the control horizon, like the prediction horizon, because here we are proposing a new control signal for a certain amount of time, and this creates us a new output, prediction horizon, let me say, how our system will behave in some certain future. So I would like to summarize the main working principle of model predictive control over this diagram here. So let's consider that we are at time frame k, and we have, of course, past signals, and we have a kind of future ahead of us. And what's happening here is that, so you see our input signal, and you see our, let's say, controlled variable output, and this is the reference signal. So we are aiming to converge to this line above with respect to the input signal that we are applying to it. So, and you see here we have this control horizon here from time is equal to k to the time is equal to k plus nu. U is the input signal, so this means that we have the control horizon until this period, and then maybe it could be larger than the control horizon. We have a prediction horizon, so until when we are calculating our system output. So this may also be equal to each other in some cases. And we made our calculations, our optimization routines, and determined the control signal, UK. We are applying it, but in the next time frame, most of the time, of course, it depends on your how you set the implementation of model predictive control. You can also continue this with this planned one for a certain amount of time, but in the next time frame, in the k plus 1, we are again calculating the optimal sequence again based on the current system states, and for example, we may end up with another variable than the previously planned one, let's say uk plus 1 here, and yeah, maybe we have now a different scheme here. So this is more or less how model predictive control works and the main terms that we need to know initially. Okay, by this way I would like to conclude this section of our lecture, and in the next one we are going to dig deeper into the mathematical formulation of MPCs.